plastics that we're currently making and that are ending up in the environment, and the potential contamination from those plastics into animals, plants, and our aquatic soil systems, and then ultimately into humans. Yesterday there was a fantastic talk by Jenna Jamback, and she talked about plastics and microplastics around the world and in the oceans, and the total amount of plastics produced in the world last year was 8.6 million metric tons, which is a massive amount. So some of the ingredients in these plastics are things like plasticizers, like BPA. So here I have BPA, a little description of it. It's been mass produced in various plastics and resins. So it is in everything from plastic cups, or it used to be, plastic cups, disposable cups, water bottles, like we have here. Also things like dental seats, sports equipment, CD covers, thermal receipt paper, resins, laminate flooring, medical and sports equipment. It's literally in all kinds of consumer products. So because there's a lot of there's been a lot of science on this over the last 2 decades, and a lot of public and scientific activism. So now a lot of companies are actually using sort of next generation alternatives, BPA alternatives, things like BPAF, and the chemicals are shown right here just for comparison. This is the parent regular compound, BPA. This is BPAF, has a set of 3 fluorides, basically fluorines representing instead of the methyl groups, which makes it potentially a little bit more reactive. And then also we have 17-beta estradiol, which is a very common estrogen in vertebrates, including humans. And we also looked at DBP. So the thing is that many companies are actually starting to replace BPA with some of these other BPA alternatives, like BPAF. And it can still say, if you look at the bottom of plastics, it'll say BPA free. But that does not necessarily mean that it's BPAF or BPS or some of these alternatives, that it's free of those. So actually it's sort of a brilliant marketing strategy where they can say BPA free, but it might have some of these other things. Okay, so myself and my students, who are sitting right here, and several other students at St. Mary's, we've been looking at this question: what are the effects of BPA and BPA alternatives that are commonly being used? What are their effects on early cell division in the early embryo, and the effects on survival in the early embryo? So we use the African clawed frog, or Xenophus laevis. This is a nice model system because they have very large eggs, large embryos, and we can expose them to various things and do nice toxicology estimates. So the goals really, at the objectives level, is to examine early exposure to these chemicals from immediately after fertilization through 96 hours of development, and then compare their toxicity, potency, and teratogenicity, or what kind of embryonic effects they have on an organism. And hopefully this will allow us to gain potential cellular and embryonic effects of these common plasticizers on human development. So it's a really nice model system. So the basic methods: we obtain gametes from adult male and female frogs. We do IVF, in vitro fertilizations, in the dish, and then we expose them to various concentrations of these plasticizers, from low to higher doses. We stage them because development has been very well characterized, and then we image them on an inverted stereoscope and take lots of pictures and video and sort of assess exactly what might be going wrong at various stages of development. So just to go right to the results, what we find is pretty shocking. The BPA results are similar to what other groups have found in various species, various vertebrates, including mammals. BPA actually, if you increase the dose, so this is going from about half an hour to 72 hours at increasing doses of the compound, the arrows are sort of indicating more and more developmental defects as time goes on, or exposure goes on. Here's a normal control state going across the top row compared to the higher doses of BPA. And hopefully what you could see, this is a nice normal long body axis, normal head. It gets shorter, they get less pigment, they get various neural fold, so that's the early spinal cord that's starting to develop. There's all kinds of aberrations that then get realized later in development as well. And actually higher doses lead to absolutely no survival at all. So what really hasn't been looked at is these alternatives like BPAs, which, remember, can be in some of these compounds, some of these consumer products that are labeled BPA free. So we went into it, we looked, we did a dose response. We went very low, actually. We went to nanomolar range, and we ended up still finding aberrations that were very similar to the BPA effects: neurological, neural fold problems, lack of survival, bent, shorter tails, improper head-eye development, and body access, overall gross body access defects. So we wanted to quantify that. So that was all sort of qualitative measurements, doing a lot of imaging and microscopy. We quantified this and we looked at the percent of normal embryos from 2 to 12 to 72 hours for increasing doses of BPA, comparing it to estradiol, which we have here as E2, and then also to various increasing doses of BPAF. And hopefully what you can see, there's a lot of numbers and bars here. The control is always in black. What you can see is there's this distinct trend of downward sort of loss of normal embryos as concentration and as time go on. The asterisks indicate statistical significance. And hopefully what you can see is that we can go to low doses, 30 nanomolar of BPAF, 300 nanomolar, and get very similar, if not greater, effects on embryo development. So going further, we wanted to look really closely at the beginning, because many people that have looked at BPA across various vertebrate species, they tend to look a little later. They don't look right at the beginning. Embryo development from the sperm and the egg going from 1 cell up to 100 cells or so. So we looked at this very earliest snapshot, or this window,